And actually, we have, I think, 3 approaches that we will show you today how you can tune your controller based on the border plot. First of all, let me tell you what should our border plot look like? How do we like to have our final border plot? Well, it's quite typical to have a border plot which shows a negative slope, which shows a amplitude that goes lower and lower and lower with increasing frequencies. We want a border plot that goes through 0 decibels at a quite high frequency. The higher the frequency we go to 0 decibels, the faster your system is. So we want a high bandwidth. And then after 0 decibels, we want to get very negative gain values. That means that we will not amplify the noise at all. We will diminish the noise as much as possible. And what's also important is that at 0 decibels, we're far away, we're enough far from the minus 180 degrees, because a border plot which goes through 0 decibels and has a phase lag of minus 180 degrees or more results in an unstable system. We should avoid that at all costs. And all the methods we will see are designed specifically to do that. Make a bandwidth which is as high as possible to have a dynamic system, and at the same time keep as high as possible above minus 180 degrees to have a robust controller, to have a controller which is for sure not leading to unstable behavior. Let's take a look at one possible approach. One possible approach is purely based on this phase margin. So what you do actually is you have your border plot, you have a certain desired phase margin. Typical value can be 45 degrees. I will show you the values in the next slide, but typical value for your phase margin is 45 degrees. Well, then you go and look for the point where you have minus 150 plus the phase margin. So in this case, this would be minus 105 degrees. You search for that point with the data cursor. You see the frequency at that point, and you also see the gain at that point. Those are the only 2 values, frequency and gain, that you need to put in an Excel worksheet. That Excel worksheet is sent to you. You can use it to design your controller. And that's very nice. This means a border plot, which you know by now how to measure, and a desired phase margin is enough to design a PI controller with good performance in a very rational and thought-through way. You don't need trial and error anymore. You don't need to auto-tuner anymore. You don't even need a relay feedback experiment. You measure the boat characteristic. If you have the boat characteristic, you are able to design a very good PI controller with the Excel worksheet we've sent to you. What's even more, you will see in that Excel worksheet that you also have the output for cases where you want to design just a P controller, or where you want to design a PID controller. Here I only show the PI, but in the Excel worksheet, you also have the possibility to design a PI, PID. You even have the possibility to come to parameters which are not in this format. Some are in other formats. Maybe one of my colleagues can open the Excel sheet. I don't know if they hear me. Maybe one of my colleagues who's listening right now can raise his hand to indicate that he heard that I want to see the Excel sheet. They're not listening to me anymore, so I just continue, and I'm sure we will see the Excel right away. So maybe Abdel can open the Excel sheet to show it, and I will give the word to him so that we see the Excel sheet. Okay, but I talked about phase margin. What to choose for the phase margin? Well, you see here we chosen different values. 100 degrees, quite large. You see that this system is very stable, but we have a slow system. If you make the desired phase margin too large, you will have a slower system. If you make the desired phase margin too low, you will have lots of overshoot. And luckily, in this case, it's not a rule of thumb with limited reliability. This rule of thumb is valid for almost any case. Larger phase margin, slower, very stable system, very robust system, but maybe too slow. Low phase margin, very fast system, but maybe too aggressive. So you have to find the sweet spot in between there. That can also be a little bit of trial and error, but at least you know for sure if you apply this method, if you apply the Excel worksheet, that you get the good results. Let us take a look at that Excel worksheet. Abdel will share its screen, but he does not need to share his microphone. I will give the explanation worksheet. So what you see here, that's the relay feedback experiment. In the first step, here we have the phase margin experiment. So you see, if you want to design different kinds of controller, P controller, how you can do it. Then you see PI controller, you have to start from a different phase, -150, plus the phase margin. For the PID controller, more below, it's even different. You have to start from minus 217 plus the phase margin to design your controller, but you get all the values immediately and you can put them in your drive software. Okay, I will retake the screen because I will share with you another approach. This first approach is based on phase margin. Well, actually, if we have a motion system with resonance and an anti-resonance, we might not need the phase margin. First, something else. Now you see that based on phase margin, based on the Excel worksheet, we were able to design our PI controller. We have good settings for the PI controller. We can be sure that it's a stable system. But we don't have a positioning system yet. If we want to design a positioning system, we have to cascade a position control loop around our speed control. And that position control loop takes the desired position, subtracts the actual position from that, send it to a proportional gain, and that proportional gain will define the desired speed. And that desired speed will at his turn command the speed control system. Well, of course, if we do it like this, you see there's only a P controller. Why is that? Like I told you, do not use an integral action if you don't need an integral action. The integral action is not always necessary, and if you don't need the integral action, it's actually an advantage because it's a parameter that you don't have to set up, and also it decreases the risk of getting an unstable system. Why do I know that I don't need an integral action for the position control? Well, it's very simple. Just ask yourself the question, can the output of my controller become 0 if my error is 0? So if our error is 0, our desired position is reached, then our speed set point becomes 0. And that's good, because if we reach our desired point, our speed set point has to be 0. In that case, you don't need an integral action. Let's apply this reasoning on the speed controller. On the speed controller, once again, you have the desired speed and you have the actual speed. You subtract the actual speed from the desired speed. You get the speed error. You send the speed error to a PI controller. And the question now is, can the output of my controller be 0 if I reached the desired speed? If you reach the desired speed, you still need a current to drive the system. So here, the output of your controller cannot be 0 if the error going inside your controller is 0. In that case, you need an integral action. In the case of the position control, when you reach your desired position, you don't need an output of your controller anymore. The output of your controller can be 0. If that is the case, if the output of your controller can be 0, if the input is 0, then you don't need an integral action and you don't use it. How do you set up a pure proportional gain? Well, you can apply the techniques we saw, measure a Bode plot reaching from desired speed to actual position at the output, apply our methods. But if you only have one parameter to play with, it's much easier. You take a low value for Kp and you increase that value for Kp to see that you get a better displacement, that you get better behavior. If you see that suddenly you start to have overshoot, you stop increasing your proportional gain. So you increase your proportional gain just before the point you start having overshoot. This is something you can easily do with trial and error. Start with a very low Kp and just increase it. But you can only do that if you only need a proportional controller, and that is not always the case. It's a minority of the cases where you don't need an integrator, but if you don't need it, it's a big advantage. Okay, I have one approach now to design my controller. Let's look at the second approach, because the phase margin is very interesting. It's generally applicable on all kinds of systems, but it might be difficult to have a good idea what is the desired phase margin. 45 degrees, more or less. It also involves some trial and error. When you have a mechanical system with a flexible coupling, you will most certainly see an anti-resonance and a resonance frequency. And those frequencies we want to avoid, actually, because at the anti-resonance, it means that at your motor side, because we have our encoder at the motor side, we don't have the encoder at the load. Your motor side, you're putting lots of energy in it, but your motor doesn't move anymore. Your load is moving quite heavily because there's a flexible coupling, but you don't detect it with your encoder because you're measuring at the side of the motor. And we want to avoid such frequencies. That can lead to instability, large vibrations, etc. So what we do is we design our controller to work 6 times below our anti-resonance frequency. You see the anti-resonance frequency in the Bode characteristic. You divide that frequency by 6, and then you have a frequency at which you can design your controller. You can take the measured frequency, put it in the Excel sheet. You can take the amplitude, put it in the Excel sheet as well, and then you get the output for the TI. You get the desired T and the desired Kp. We can also use that for a PID controller. We can also use that for a P controller. It's all in our Excel sheet that is provided to you. By applying this on the cases here in the lab, we saw that we get a velocity response like this. So from a velocity of 0 rotations per minute, required velocity of 0 rotations per minute, to a velocity of 500 rotations per minute, you get a response like this. This is not a very good response. You get a high overshoot, but your system reacts quite quickly. Is that a problem that we get a high overshoot? Not necessarily, because we will not apply a step on your velocity. You will not start with a requirement of 0 rotations per minute and suddenly 500 rotations per minute. It's your position controller. If we go back, it's the position controller that defines the speed set point, and that speed set point can increase slowly and then decrease slowly. So we don't apply an actual step here. We might apply a step on the position control loop, but most probably we apply a trajectory there. So we don't have to be afraid about this overshoot because we will not just apply a step. And we know for sure if we keep 6 times lower than the anti-resonance frequency that you actually will have a quite stable system, that you can rely on our worksheet to have stable values, to have a stable output. We passed 6 o'clock, sorry for that, but I will still take the time to explain approach number 3. It's also actually the last approach. It's the last thing I wanted to explain to you. So then afterwards, if people have to leave, we completely understand. But you know for sure right now already that you're able to measure a Bode characteristic. Well, actually all the approaches I'm explaining all rely on the Bode characteristic. Just look at the characteristic, like here as well. You see the input, the required torque or the required current. You see the output, the speed. You use that input-output relationship to plot a Bode characteristic. That Bode characteristic gives you an anti-resonance and a resonance frequency. Here again, you just use the data cursor in Siemens Starter to identify the frequency at which you have the anti-resonance, to identify the amplitude at which you have the anti-resonance, and you can also see the frequency at which you have the resonance and the amplitude at which you have the anti-resonance. Those parameters are very valuable. This approach number 3 is something typical for our Tetra project in OptiMotion, because here we especially look to positioning applications. In positioning applications, it's very typical to have a motor inertia, a flexible coupling of some sorts, and then a load inertia, and then you get a boat characteristic like that, with its outspoken anti-resonance, with its outspoken resonance, and based on those parameters, you can actually design not only a controller, but also a filter. And that's quite interesting. Why would we take that resonance frequency for granted? And why wouldn't we apply a technique where we filter out that frequency? Well, Siemens Starter has standard notch filter capabilities and other drive software as well, because it's quite common for such cases that you want to filter out the resonance frequency. And that is done with the so-called notch filter. So you see here, notch filter, we can actually set it up. We can actually set it up in Siemens Starter. You can choose for a so-called band stop filter, and you see here what this filter does. It decreases the signals with this frequency, so it cancels out the resonance frequency. Your notch filter should be designed with a certain frequency. Well, let's take just the same frequency as here, the resonance frequency you measured. In this case, 539 Hertz. You're able to measure the boat, so then you're able to design the bandstop filter in a very thought-through way. The notch filter also needs a certain bandwidth. That bandwidth is chosen preferably equal to the resonance frequency, or maybe up to 2 times the resonance frequency, somewhere in between there. That's what we propose based on experience on the setups. And then the notch filter also needs a certain depth. There are notch filters with infinite depth. We saw on the setups that you get much better results with a finite depth notch filter. So it has to be a negative value, because you have to decrease those frequencies, and that value is actually the resonance amplitude minus the anti-resonance amplitude divided by 2. That's what we propose, then you get good results. Okay, so we're able to design notch filter. By the way, if you have an application and there is no standard capabilities of notch filters, you can also program it yourself. I will not go into detail of that, but actually programming your program a notch filter yourself is quite easy, because we also provide a worksheet where you just have to give in notch filter depth, which is equal to anti-resonance minus anti-resonance divided by 2, notch filter frequency, which was equal to the resonance frequency, notch filter bandwidth, which was also equal to the notch filter frequency. You put in these values as the input, and you get right parameters for the notch filter algorithm. And that notch filter algorithm is something you can just program. You can program in your system the notch filter algorithm like this. The parameters are calculated based on this worksheet, and then you have the good notch filter in your system. So that's for if that system doesn't provide you the opportunity to do that. In Siemens Starter, it is possible. Once we apply the notch filter, we have to redo the boat measurement. We have to do the boat measurement another time, and then we will also see that the resonance frequency is actually decreased, filtered out by the notch filter, which is a big advantage. Then we have a new boat characteristic, and that new boat characteristic, the purple one, which is of the system and the notch filter together, well, that new characteristic can be used to design the controller. How will we do that? Well, we do it step by step. We go first to the point at which we have a phase of minus 180 degrees. That's also the point at which you have this shift, because actually that point and that point only differ 360 degrees. in geometrical terms, that's just the same. So you start at identifying the point at which you have minus 180 degrees. That's the point at which you have the shift. Then we go up to the amplitude characteristic, and there you see a certain value, AMO, or AM0, the amplitude margin in the first case, just when we haven't applied a controller, we have already an amplitude margin, that's that value. Just remember AM0. You add 10 decibels to that value, you look for AM0 and you add 10 decibels to that, and then you get a certain value here. So just we took AM0 plus 10 decibels, here have a certain frequency. That frequency actually is important. That frequency is a value which we have to write down and which we will put in our Excel worksheet. At that particular frequency, you also have a particular phase. That's also a value which you have to write down. And once again, with those two values, you can use an Excel worksheet we made for you to design your controller. So that's very convenient. You don't have to do the mathematical calculations yourself. The Excel worksheets are there to help you. Just start at, short recap, start at minus 180 degrees, look for the amplitude margin in that case, add 10 decibels to that value and look for the lowest frequency in which you have that. You could say, it's the lowest frequency at which you have that, and or the highest, sorry, this frequency. You identify that frequency, write it down. You look to the phase at that frequency, write it down. And then with those values, that's something you can put in the formulas. You don't have to apply the formulas. It's all in the Excel worksheet. The only thing you need is, like we said, the amplitude over there, the frequency over there, and the phase over there. That's all needed in formulas. When we put it in the formulas, these give us a good TI and a good KP. Another thing that the formulas require is a desired phase margin. So the advantage of this method is that you can still play with the phase margin. As you know, if you will choose 40 degrees as phase margin, you will have maybe a very aggressive system, responding very rapidly, but maybe too aggressive. If you choose for 80 degrees, it's a very robust system, very damped, but maybe too much damped. So you still have the freedom to choose a value in between 40 degrees and 80 degrees and put it in the algorithm. All right, this method actually requires to check again if the both characteristic of your system with the PI controller you designed and the notch filter and the system, if that is like you desired. And how can we see that? Well, we have to look for the phase margin. The phase margin is the phase we have at 0 decibels. At 0 decibels, you have a certain value above minus 180 degrees. So the difference between here, minus 117 and minus 180 is 62.9 degrees. That's lower than what we required ourselves. We asked for a phase margin of 70 degrees. We get a phase margin of 62.9 degrees. That's not what we wanted. Okay, then just redo the calculation, and instead of asking for 70 degrees, we ask for 77.1 degrees. So the difference in what we desired and what we obtained, we compensate that in our new desired value. We put that in the formulas, and you will get the good phase margin. And then you get the final design. Of course, we also have the auto tuner. I will go through that. Auto tuner has, of course, lots of advantages. It can give you good performance. It means you don't have to do anything yourself. You do not need to measure both. It's a fast method. Disadvantage is that it is not always available. Not all drives have auto-tuning methods, and auto-tuning does not necessarily give you good results. On one of the setups here, our auto-tuning gives us an unstable an unstable response. That's because the flexibility is too large and the autotuner cannot handle that. So in most cases, autotuners also don't are not applicable in all cases. They also have a limited viability, a limited range in which they give good results. We saw also with our OptiMotion method that we get results that are slightly better than the autotuner in starter. So this method can be a little bit better. So it's very good when you are able to measure a boat characteristic and you have our Excel worksheet, you have actually multiple methods to apply. So this is my concluding slide, actually. The relay feedback method, it's applicable on all kinds of cases. It can give you a good P, a good PI, even a good PID controller. Of course, in electrical motor applications, we don't use the D controller because it gets unstable, it amplifies the noise too much, but relay feedback is applicable. The phase margin method is applicable. The anti-resonance method I've shown, approach number 2, in which we take the anti-resonance and we take a value of 6 times below that, is also applicable. We cannot use that to design a PID controller, but that's not an issue, I think. Actually, this cross has to stand here because we cannot use the OptiMotion method to design a PID controller, so these have to be switched, but I'm sure this will be corrected in the final edit of the video. And then we also have the autotune method, which can also give you a PID, but is not always applicable. So actually, phase margin, anti-resonance, OptiMotion, these are 3 methods that you can do yourself if you have a boat characteristic that can give you very good results. You can do it yourself. You can measure boat in any kind of cases. Before I give the floor to Santiago so he can show you the final demonstration, I'm quite interested in the fact if you will try out our methods or not. If you want to try out our methods or not, I will once again share a poll so that you can choose. Okay, so now you should be able to choose between option 1, eager to find out, option 2, you will still use the methods you use nowadays, or option number 3, you're not sure yet, maybe you want to wait for the demonstration of Santiago to make a final choice. I also see here that you're nicely divided, or you want to wait for the demonstration. So I see that all industrial partners filled in their application. So it's a very nuanced audience, actually. So, like I said, we're running over time. I explained everything you need to know from a theoretical basis. You know enough. You know where to use a D controller and where not to use a D controller. You know where to use an I controller, where to use not an I controller. You know you always have to apply anti-wind-up if you can apply anti-wind-up. And most importantly, you know how to identify a Bode plot of a system. And if you have a Bode plot of your system, you're perfectly capable. You can really say, wir schaffen das. You're perfectly capable. Yes, we can. We can actually design our controller. You get the worksheets we provided you. In the worksheets, you can apply the phase margin method, the anti-resonance method, and also the OptiMotion method. And everything we said today will be provided in video clips, so you can re-watch if necessary. I give the floor now to Santiago. He will actually apply the OptiMotion method on one of the setups here in the lab, and then based on the timing, we can see if it's still possible to let you experiment yourself or not. Okay, thank you very much. And Santiago, you have the...
Okay, now we go again to starter. So this is the boat plot for the setup I am using. It is similar to the one that you got when you did the second hands-on. So the idea here is to identify the resonance frequency first. So we go to the cursor here, we pick up the resonance frequency. Here at the bottom of the screen, we can read the value for that point and the frequency. Actually, here we see that the frequency is 746. Now here we have the anti-resonance frequency, it's around 351, and the magnitude at that point. So the software itself also compute the difference between both cursors. So here actually we have the difference in amplitude between the resonance frequency and the anti-resonance frequency. Now we can use that value and divide it by 2 as explained during the presentation, and that will be the depth of our notch filter. Now we will add the notch filter to the controller or to the system or the loop. First we go here in open loop closed loop control, we go to current set point filter. We will select set point filter 2. We click on that. Then this interface will appear. We go here and we select band stop. We use our notch frequency as the resonance frequency. In this case was 746. We will use the same bandwidth and our depth, which was minus 19.2. Reduction will be 0. We accept, and then we tick here in filter effective, so the filter will take effect. Then we close the window. We can see here that our filter already appeared. Now we will go again to device trace. We make sure that we have the right signal stick, so we have the speed and the set point torque, the current set point torque generator, which is what we need. We need the torque against velocity. We have here transfer. The first one, the signal 9, we must tick that one. It's important to mention that this signal has already the scale that is needed for the units. As is during the presentation, Sten explained that the controllers units are different from the one that we have here in the starter. We have RPMs, and the control units, as you can see here, are in Newton meter per second over radians. So we have radians seconds here. So here we already scale the values. Now we check in the function generator that we have a PRBS signal and that we are in current set point before filter. We can assume control priority to do the vote again. And we can start the drive. Then we will start the measurement. And here we will tick on the trace. So we can see that it sent us to the time diagram, but we need the bow diagram. So we will go to the bow diagram tab, and we can see how the filter suppress the resonance peak. Now we will use this to design our system. So we will again use the cursor. So we go here, we tick in the cursor. We will go in the phase graph or curve to the point in which the first point in which have the graph of the phase or the jump. So we can zoom it just clicking here, holding the mouse. Then we will see that this is the value here. So in that value we have minus 5.8 decibels. So we take that value and we add 10, and then we end up with 4.2. Now we will go here in the magnitude curve with the other cursor, and we will find this magnitude, 4.2. So here we will move our cursor until it's somewhere here. We see that due to the resolution, we cannot achieve the exact value. So we have either 3.9 or 4.9. So we will go to the higher value just when we cross to the higher value. Sorry. And then we will take that point for the design. Now we can go to the Excel. We go to OptiMotion tab, and we will introduce the values to get the gains. So here we see that our frequency is here at this point, because we are using this cursor. Our frequency is 78.23. So we introduce that value here. Then we also introduce the amplitude. So the amplitude there will be, wait, the cursor move. When, no, no, it's here the point, sorry, correct that. So we have frequency 78.1. The amplitude is 4.9. And we check the phase at that point. So here is minus 103.5. Minus 100.5. Let's say that we want to achieve 70 degrees as a phase margin. So we add here, we insert here the value that we want to achieve, and then we scroll down until the PI controller. So here we have the gains, KP and TI. Taking into account that TI is in seconds, the units. So we will introduce first the KP gain. So we'll go again. We go to speed controller and we introduce here the value. The units are already the right units because we scale the both. And here we have seconds and starter ask for milliseconds. So we multiply this value for 1000, so we will have 17.88. Okay, now we can go to the device trace again, and we go to trace. In this case, we will check if our controller achieves the result we want or the design criteria. So the output will still be the same, but the input for the for this board will be the error because we want to include the controller here in this board also. So you see that this transfer get turned into a red one. So that means that it will be an error because that signal is not more available. So we untick that signal number 9 and we tick number 10, which will do a transfer function between the 3 as an input and the 1 as an output. That what we need. Here, these parameters doesn't change because we will use a factor of 1 and immediate record. Then we move to the function generator tab. We need now to do a speed set point before filter because we are now including the PI controller. So this both will be performed with a PRBS signal on a speed. Here we can use 50 as a maximum or upper limit. Our amplitude is 20. So we will switch between 20 and minus 20. And here we will have negative 50 as a lower limit. So now we already set our PRBS signal, so we can proceed to measure the boat. So we go again, the drive on, we start the motor, and we start the trace. Then we stop the drive, so the motor stop. Then we go to boat diagram, and here we can see our boat. Now we again take the cursor, the X cursor, and we will check our phase margin and amplitude margin. So first we will check the amplitude margin. For that we go again to the point in which we find the jump on phase. So it's here. We see that for that point we have minus 10.2 decibels, which is lower than minus 10. So we are achieving that criteria. So we fulfill the first criterion. Then we will measure our phase margin. So we will go to the point in which we have 0 decibels. Actually, here by luck we have the exactly point. In case you can't find the exactly point due to interpolation or to the sampling, just go to the nearest lower value. But here we are okay because we found out that we have 0.0. Our phase at that point is minus 107.7. So we take 180 and we subtract that value, And we can see that our phase margin is 72.3, which is actually close to the 70 that we wanted to achieve, but it's good enough because it's higher than 70. So the higher, the better the response in this case, because we are more interested on the overshoot, but the system itself is fast enough due to the characteristic of the servo motor. So we want to achieve overshoot, so a higher phase margin will be better. So we need at least 70 and we achieve 72. So the system, the design is okay. Now we will test how the system looks like, or how the response looks like with this controller. So we move again to function generator. We will use a speed set point before a filter. Again, it's a step response that we need to produce. So we select rectangular for the signal type. We will move to 500 RPM. So we will put it in the first box. And the lower limit will be 0. We want to switch between 500 and then 0. And we will be on or in a 500 during the half cycle. That means 0.5 seconds. Now we need also to go to trace because we don't have the right signals check. Actually, we need the output is okay, but the input will be the set point before filter, which is this signal. This signal number 10 turn again red because the signal 64 is not active anymore, but we can just untick to avoid errors. We will use a trigger this time, so a positive edge we selected, and it's stored by default because we already did it during the first hands-on. So now we have the trigger, the threshold is okay, and the pre-trigger is fine, so we can proceed to measure our response. Here we will go on, okay, again with the drive. We start the trace first, so we can see that we are waiting for the trigger, and then we start the movement of the motor. We click on yes, and we will see alone that the system already finished. Here we do undo some completely when you have the screen bad scaling, but now we can see that our signals are still doesn't have the same scale. So we go again to scaling, we adjust that, and then we will have this. So now we can see the response, which is quite good for this system in particular. We can even use the cursor for that. So if we have 500 RPM or 50 will be the 10%. So if we use a criteria of 5%, that means 25 below. So at 475, we will reach our steady state. So you can measure here, and it will be here in between, something here. So briefly, we can see that into 10 milliseconds, we achieve our steady state, which is quite fast. And the overshoot, we can see that we have almost not overshoot. We achieve a maximum value of 509 RPMs here, which is probably, if 5% will be 1%, so it, or around less than 2% actually. So here we can see the good performance of the controller on this system, and that the method work properly.